So before the break, so we introduced the semi-MDP formalism, where now we can actually deal with both axes. Okay. By the way, so I think as I mentioned for one of the questions, so all these equations hold even for primitive actions, in the sense primitive actions are temporally extended actions with time step 1, right? And very deterministically taking that action. So now we have a framework where we can actually seamlessly integrate primitive actions and macro actions together, and we have the Bellman optimality equations, and we could extend any of our algorithms that we have seen so far for this particular macro action setting, right? Now, one way to think about how yeah.
Are primitive actions MDP by themselves, or are they semi-MDP?
When you just have primitive actions, then it is an MDP. But semi-MDP is like it has a collection of primitive actions and macro actions. Okay, so now one way to differentiate how MDPs and semi-MDPs behave is here is a simple cartoon explanation. So in the case of MDPs, right? So you will be, let's say this is my time, okay, and this is my states. In the case of semi-MDP, you will, sorry, in the case of MDPs, so you are taking primitive actions, so you will be moving one step at a time. Okay, something like this. Okay. However, when you are in semi-MDP state, SMDP, you have this notion of temporally extended actions, which means you can move by skipping time, right? So let's say I take a macro action here, that might already take me here, and that might take me, let's say, here, and that might take me here, and this might take me here. Is that clear? So with just 4 macro actions, I can cover the same trajectory that was covered by probably 10 or 15 primitive actions. Is that clear? Now, the moment we are in the SMDP space, okay, so there are a lot of nice things that it promises. So for example, we can talk about the structure of the problem. Okay, now let's go back to the 4-room example that we had, which was basically this grid world with 4 different rooms and exit in the top, right? Now, the moment you start thinking about this macro actions, which tells you have to move, one option is to west room leaving abstract action or north room leaving abstract actions, right? So now you can kind of summarize the entire room into one state, right? So now this figure that you're seeing here is the same 4-room world, but summarized to only 4 states. This state is room 1, this state is room 2, this state is room 3, this state is room 4. Now, it doesn't matter which part of the room 2 you are in. So if you are in room 2, you can execute this macro action, right? So in some sense, it aids faster learning because it gives you a kind of state aggregation, things we have seen before functional approximation, right? So one of the functional approximation methods that we have seen was state aggregation, where we were kind of randomly aggregating things together. But in this case, when you have macro actions, it naturally aggregates a bunch of states together. So you are dealing with this 4-state space now instead of the original maybe 25 cross 25 state space. Yeah.
I kind of start seeing some issues with this. So we now just have 4 states, and according to that, in room 2, it doesn't matter where I am, and apparently it does matter, right, in the actual grid world. So it's my launch policy of going from room 2 to room 3 and room 1 and getting out of it might not be optimal, and I might be better go from going from room 2 to 1, 2, and then.
That's a very good observation. So the observation is like there might be problems with having this 4-state summary because like okay, well, I want to go back, but then like we will lose the camera. So let me see if I can go back as slow as possible to the I think it's a lot of slides before. Okay, yeah. Now let's go back to the same example, right? So now his point is valid in the sense it is not completely true that it doesn't matter which part of room 3 you are, right? Like so, like if you are in this particular black dot, then maybe this is the optimal thing to do. Okay. However, maybe if you are here, then maybe this is the optimal thing to do. Okay. Now, there's another complication that I can make to this grid world to make it a little bit more challenging and it will bring out this issue. Okay. Now, imagine your actions are stochastic. Okay. If you take a north, you will go north 80% of the time, or say 70% of the time. Okay. For the remaining 30%, you can go to all 3 directions with equal probability, like 10% to south, like 10% to all the 3. Okay. Now, what could happen is you're here. Okay. Now, even if you figured out that you should be going here, which is the right thing to do, by the way, it might be the case that you took an action to go here, but it brought you here. Okay. Then you took an action to go here, but it brought you here, like it brought you here. Okay. So even though this stochasticity is pulling you towards the next door, your policy might be stubborn to just reach the best door. Right. So there are many notions of suboptimality with this. Like so, like when I say there is a lot of promises, like it also comes with a lot of catch. So it is not strictly better than like the flat reinforcement learning scenario that we have seen. Okay. So in fact, how to address the shortcoming that he observed and like the new shortcoming that I mentioned here, right? Like so, these are the open problems. Like so, how do we design algorithms which can handle these suboptimalities and still get better performance? Is like it's a hard question. Like so, there's no free lunch, right? Like so, like if you want to go to higher level abstractions, like you have to lose or sacrifice something. Like so we are sacrificing some optimality here. Like so, we are going to talk in detail about like notions of optimality like in 5 minutes. Okay. So now let's go back slowly. Okay, as slowly as possible. Okay. Now, so the biggest benefit of decomposing a larger MDP into like smaller like problems is like we can have state abstractions. Okay. Now, there are many situations where we can use state abstractions. So for example, once you start dividing things into subtasks, like the individual subtask, right, like might never reach some other states. Like so, for example, like okay, well, I think I should have the figure here. Let's just take the 4-room example. Let's say this is the door, this is the door. These are doors. Okay. Now, when I am learning the policy corresponding to this particular room, I would never reach this room, right? In that sense, for that particular policy, my state space is reduced. So that is one place where you can do some sort of state abstraction. Okay. The second type of state abstraction is what I mentioned. Like so, this the aggregation thing. Like so, like it might be the case that these sub policies always take you to the door, so it doesn't really matter like what is inside the door. Like so, like all it matters is like you reach the door, right? Like so, now there are many situations like where you can have these kind of abstractions, and the hope is it is going to speed up learning. Is that clear? Okay. So now let's talk about optimality. Okay. Now, even though I was talking about a lot of benefits of doing hierarchical reinforcement learning, there are also some limitations. Okay. Now, first of all, HRL cannot guarantee in general that a decomposed problem will necessarily yield an optimal solution. Is that clear? It is in fact a much more harder problem, right? Like, so given a problem, how would you decompose it so that the solution that you're getting is the optimal solution for the like non-decomposed problem, right? Like, so that's a very hard question. Like, so now in general, there is no guarantee. Okay. So it depends on a lot of things. It depends on the problem. It depends on the quality of the decomposition. It also depends on the hierarchy of the subtasks and like how you are structuring these things. Okay. It depends on a lot of things. And if you have to learn all these things, again, that's a hard problem. Okay. So the general, like the general guarantee that we can give is like much more weaker than the optimality guarantees that we can have for flat reinforcement learning algorithms. So in the case of hierarchical algorithms, so we will talk about two notions of optimality. Okay. So like the first one is hierarchical optimality. Okay. And the second one is recursive optimality. Okay. Now, what are these? So when I say an algorithm is hierarchically optimal, okay, it means that that algorithm maximizes the overall value function consistent with the constraint imposed by the hierarchy. Okay. So if I tell you this is the hierarchy of actions, for this particular hierarchy, what is the optimal thing to do? Is that clear? So the task policy depends not only on its like sub policies, but also on the entire context. So, okay, I think I did not talk about deeper hierarchies, right? Like, so we were only talking about one macro action, and that is a set of primitive actions. Now you can extend this to like as much depth as you want. Like, so you can take one macro action. Let's say you can take one macro action. Let's just call it as A. Let's say there is some action A1, which is a macro action. Okay. Now this macro action has a bunch of possibilities. Now it could construct this temporally extended action by using some primitive actions like A1, A2, or it could in turn select another macro action, let's say A2. Okay. So for example, my A1 could be something like just A1, A1, A2, which means it is just one level hierarchy. Like I took A1, A1 took 3 primitive actions. Okay. But my A1 could have many levels of hierarchy. Like, so when I take A1, A1 might decide to call A2. Okay. Let's go see what A2 has. Like maybe A2 has A5 and some primitive actions, A3, A5. Okay. Now A2 can decide to call A5. Okay. Okay. So let's say A1 calls A2 followed by small A1 and it ends. Okay. Now, given that this is having this capital A2, okay. So let me write it here. So A2, A1. Okay. Now, I think I'm kind of confusing by capital A's and small a's. So I'm going to change my notations. Let's just call macro actions as M's. Okay. So let us say I have one macro action M1, which could take either primitive actions or some other macro actions. Okay. Now let us look at another macro action M2. Now M2 could take M4, M5, sorry, A5, A7, some random actions. Okay. Now M4, let us say that it just takes A1, A2. Now, when I take action M1, M1 might decide to just do A1, A2, then we are done. Or macro action 1 might pick M3 followed by A1, A2. Okay. So now I have to expand this M3. So let us say M3, I don't have M3 here, M2. So let's say M2. Okay. Let's say M2 picks A5, for example. So then we will substitute M2 with A5. So my macro action 1 is going to take A5, A1, A2. And you can see that A5 was not even the primitive option available for M1, but it was one level deep, right? So now we can actually have this hierarchy of options, like or macro actions, okay? Now, given that you have this hierarchy, like what is the best possible thing that you can do? So that is hierarchical optimality. Is that clear? It has a context. The context is the hierarchy. Now, first observation. Hierarchically optimal algorithms need not be better than flat optimal algorithms. Okay, sometimes it can be better, but there is no guarantee that hierarchically optimal algorithms are going to be better than. Let us just also call the original RL optimal solution as flat optimality. So flat optimality is like when you don't have any hierarchical algorithm, okay, which is the best possible optimal solution for the task. Now, hierarchical optimality is not guaranteed to be better than flat optimality. In fact, it is for most of the practical cases, it is going to be suboptimal when compared to flat optimality. Okay. Now, the recursive optimality is even more weaker form of optimality. Okay. Now, recursive optimality just says that given the sub policies for this particular node, what is the best policy? Is that clear? I want to take an action now. I have a bunch of sub policies. Like I don't care about the entire tree of policies. Like just given my children, like what is the best optimal thing that I can do? Now, as you can imagine, this is not greater than hierarchical optimality, right? Like because hierarchical optimality at least gives us the optimal solution for the whole tree structure. On the other hand, like recursive optimality is kind of greedy in the sense it just it hopes that the rest of the things is optimal. So what is the best possible optimal thing that I can do with the sub policy, right? So in general, if you have to order these optimalities, like so flat optimality is going to be greater than hierarchical optimality, which in turn is going to be greater than recursive optimality. Okay. However, we would still like recursive optimality is still preferred because one of the advantage of having recursively optimal algorithms is now you don't care about the rest. You only care about this sub policy, right? You can learn general purpose like reusable sub policies, like because you don't really care about the whole task. Like you try to do the given subtask in the best possible way. So you can repurpose this for other tasks. Yeah, question?
I kind of don't understand the difference between hierarchical and recursive optimality. Can you give some examples maybe?
Okay. Okay. I think my examples are abstract. That is the problem. So just give me a second. Maybe I have a real example. It's not here. Okay, it's here. Okay, so I think a good example is like the 4-room thing that we saw again. Like, so now with the extra stochasticity I mentioned, right? Like, so now maybe let me quickly draw it here. Okay, so let's say these are the doors. Okay, now let's say you are here. Okay, when I say an algorithm is hierarchically optimal, okay, it means that the sub policy is not just dependent on the current scenario, it is dependent on the entire hierarchy. Okay, so in other words, it cares about the final task. So my hierarchically optimal algorithm would always tell me to go here because this is the shortest. Okay, if there is a stochasticity in the world, then like I might get drifted. Okay, but my hierarchically optimal algorithm would still ask me to go to the left, because if I consider the whole hierarchy, like from the current state, like so that was the shortest. On the other hand, like a flat optimal reinforcement learning algorithm will adapt its policy after reaching here, because then it is considering the whole sequence, like it is not considering the subtasks. So it will just go through the other door. Is that clear?
What would the recursive?
Okay, recursively optimal example.
I mean, I already understood the difference between flat and hierarchical.
Okay.
Sue was with hierarchical and
Okay. Well, okay, maybe it will become easier after we see a couple of algorithms. But if I have to give you an intuitive explanation, right? Like, so recursively optimal algorithms, like, so would, first of all, not even care about the rest of the path. It will just focus on the current task. Like, it is weaker than hierarchically optimal algorithms in the sense hierarchically optimal algorithms would still consider the path in the tree, but recursively optimal algorithms like would just focus on the current state. If I have to give a very solid example like this grid wall, I have to think about it. I'll get back to you. Okay. Any other questions? So there are a couple of questions in the chat that I missed. I'm going to take that, but any other questions here? Okay, so there was a question in the chat. So how do we handle the fact there's an infinite number of possible n? For example, the agent can turn in circles. Okay, so we assume that these macro actions are going to end. Okay, so n cannot be infinity. But how to handle that much more elegantly with the equations, I think it's a bit difficult. Like, so we will not do that for this course. Yeah.
You said we can subdivide the hierarchical into the next level hierarchy. Right? So, for
Yes.
example, if now we have 4 rooms, I can split each room into sub-rooms.
Yes.
So, at some point, we will reach like from semi-MDT, we'll reach MDT. Right? If we keep on dividing it into smaller subtasks.
Yes.
So, what is the right point to stop considering the granularity of the subtask?
Okay. So we don't know. Okay. And like, first of all, like even learning just 2-level hierarchy of options or macro actions is hard. Like, so we don't have a good algorithm to do that. If somebody is giving you the, okay, there are 2 scenarios. Okay. One is a complete learning scenario where you are automatically learning these abstract actions and you're learning this hierarchy and you're learning how to use the hierarchy. Okay, so that is the hard case. However, for a lot of practical, like, so this is for people who want to develop general purpose algorithms, right? Like, so now imagine like you care about just one problem. Like, as a company, like maybe you're working on this problem, and that is the only problem that is giving you money. You don't mind spending money to get 20 people to sit together and write this hierarchical action. Okay, by all means you can do that. If you do that, then the question of what is the extended action, like what is the hierarchy, is like removed, right? Like, so you just need to do SMDP learning. Then it is a really easy problem in the sense like you can just extend any algorithm to SMDP and it is going to work. So the moment you start thinking about how to extend the hierarchy or like how to first of all come up with the hierarchy, that is a very difficult question. Okay, so I think given this context, now we can finally see like some example algorithms like which would do hierarchical reinforcement learning. Okay, again, these algorithms, for these algorithms, we are going to assume that the macro actions are given. Okay, so there are I think roughly 3 or 4 approaches that people have attempted to design hierarchical reinforcement learning algorithms. Okay, but for today's lecture, we will see 2 representative algorithms. Okay, so the first algorithm that we are going to see is called options framework by Sutton et al. 1999. Okay, so what are options? Okay, so options are basically macro actions that I said, like it's just the names are different, but we are going to define a formalism for that, and we will also see how to do Q learning with options. Okay, now an option, let's consider the original MDP. So in the case of MDP, we had the notion of state, action, transition function, and reward. Right, an MDP can be represented by state, set of states, set of actions, transition function, and reward function. Right, like so. Now an option can be represented as a triple. Okay, so I, pi, and beta. Okay, where I is a subset of states. We are going to call this as initiation set. Yeah. Transition function. It's the probability of next state given the current state, an action. Okay, so I is my initiation set. Okay, it's a subset of states. So this is a subset of states where I can actually apply this action. Okay, so let's say I am in state 10. If state 10 is in I, then this option is available to apply. Otherwise, this is not available to apply. Okay, to give you an example, let's say, let's go back to the 4-room world. I think we are heavily exploiting this 4-room world today. So now let us say we are here. Okay, for this room, there is no south door, right? So you just don't have this option of exiting through south door. So the initiation set for south door will not have this rooms or this rooms. It will have this and this rooms. Is that clear? So that is my initiation set. Then I have my pi, okay, which is the policy for that option. So once I start the option, I'm going to follow this policy pi to do the temporally extended action. So this is given a state and action, it's going to give me some value. So this is the policy that I'm going to follow for after taking this option. And beta, which is from state to 0 or 1, is a termination condition. Okay, so the way in which I'm going to execute this option is, let us say I reach a state, I want to take this option. Okay, I will start the option and start following the policy. The policy will tell me, okay, take this action, and I reach a state where beta is equal to 1. It means that it is time for the option to terminate. Okay, so then you will give the control back to the higher level reinforcement learning agent. Is that clear? Yeah.
Is the output of beta binary or it's an interval?
The output of beta is a binary or interval. Okay, it could be either. So we can deal with both. So for example, like I think in modern like deep reinforcement learning version of options, like so your beta is going to be modeled by a neural network. which will output like whether you have to stop now or not. Yeah. Yeah, it's a probability of stopping. So it is kind of like gamma, right? Like, so if one way to think about gamma is like it's a soft way of saying when to stop, right? So with probability gamma, like you proceed with probability 1 minus gamma, like you stop, kind of like that. Okay, so okay, now is this clear? Like the definition of option. Now there are two types of options. Okay, so Markov options and semi-Markov options. Okay, now what are Markov options? So when the policies and termination depend only on the current state, okay, we're going to call that as Markov option. So in Markov option, you can start your option here. Maybe you're moving like this, moving like this, moving like this, moving like this. Okay, so from this particular state, the probability of termination or probability of taking the next action depends just on this state. So that is Markov option. Semi-Markov option, on the other hand, like let's say you are like here, the probability of termination on the next state would actually be dependent on this entire trajectory from the beginning of the option. Is that clear? Now, to give you an example, right? Like, so let us say that we take temporally extended actions, but with a counter. So we have a hard time limit of only 5 seconds for this option. Okay, so that is a semi-Markov option, because now you need a counter which counts the total number of steps elapsed so far. When it is 5 seconds, you stop. That cannot be modeled by a Markov option, because Markov option cannot remember how many steps has been taken so far. Is that clear? Any question? Okay, now the primitive actions are also options. Okay, and the primitive action A is going to be a triple where the initiation set is given by all the states, because I can take this primitive action wherever I want. Okay, it's not a subset of yes. Similarly, the policy for this primitive action is just to always take this action, right? Like there's only one action to take, and the termination for this primitive action is always 1. Like you take this primitive action and then you stop. It's a trivial option. Okay, so this is true for all S belonging to capital S. Is that clear? So now you can actually unify options with primitive actions and put all these things together. Okay, and since primitive actions are just a special case of options, now you can have an option calling another option, calling another option, then calling the primitive action. Like you can have this recursive calls like possible. Is that clear? Okay, now as I mentioned before, like we're going to assume that somebody gave us these options. Okay, like which means somebody gave us the triples, like what is the initiation set for the action, what policy to take for this option, and like when to stop, right? So imagine like one way to do this is like, let's take the 4-world example. We can actually learn individual oral problems separately and keep those policies as the policies of these options. Okay, so we can learn them, okay, if you want to, or it can also be given, like somebody can give you a heuristic for that particular option. Okay, so this is possible in a lot of robotics application. Like if you want robots to work to a decent extent, right? Like so now, like the manufacturer of the robot can give you a bunch of higher level options. Like instead of you worrying about moving with this speed, like moving like in this angle and so on, the manufacturer can give you a library of higher level options. So for example, like it could have a turn left. Okay, here's an interesting thing. In grid world, turning left is 1 step, right? But for a robot, turning left is not a 1-step action. Like so, it involves a series of motion. to run here, right? So now the moment you start modeling all these angular actions, like then it is going to become a very long reinforcement learning problem. So this is where options are useful. Like so the manufacturer can give you a library of options which might have turn left, right? And he can even give you like some complex options. Like so, for example, let's say it's a kitchen robot. There might be an option to there might be a parameterized option which is called pickup. Now you send a value to this pickup option, like for example, pick up coffee mug. So then it will find the coffee mug, pick it up. This is all one action, like one big abstract action. Is that clear? Any questions? Okay, so now that we have defined option, like now we can extend some of the learning algorithms to learn options. But before